So first of all, I would like to thank the hosts of this seminar to have invited me. I'm gladly contributing to this open source outreach initiative, which is really great, and I've been following since COVID times. So today I will talk about the work I've done during my PhD research. It was a year ago. I wrapped the project up, and interestingly, and as opposed to the first two presenters, we're moving to higher latitudes in the Barents Sea, above the Arctic circles, and actually, rather than active rift, I'm moving on to a rifted system, so something that has been break up a long time ago. So this is magnetotelluric investigation of a rifted system in and applied to the Southwest Barents Sea. So this work has been done at Volcanic Basin Energy Research and at the Department of Geoscience at the University of Oslo. So I thank all the collaborators that have been working on this project with me. So I thought first I could show a quick movie showing actually what is magnetotelluric for people that don't know much about it. So what you can see here is our planet Earth, and it's a magnetic field that's being disturbed by solar activity. Often it gives rise to northern lights that you all know, but actually what you know from the Maxwell induction law, which is the only equation I will show you in this presentation, is that a changing magnetic field gives rise to an electric field. And actually these currents can propagate in the Earth, and magnetotelluric is actually this study of the solid Earth response to a changing geomagnetic field. So, so down on Earth, on the surface of Earth, so how do we collect this EM data, especially in a marine setting? So what you could see here is a boat that's dropping receiver on the seabed, and they are left there to record the natural electromagnetic field. So as I was telling you, this is the playground, the Southwest Barents Sea. You see, this is, if I can. So this is Norway here. So we are here in the southwestern part of the Barents Sea. You have Svalbard here, Novaya Zemlya here. So the geological context is rather different from what you saw in the rifting in East Africa in the first two presentations. Is actually in the context of the North Atlantic, the breakup occurred in Eocene time. So which means 55 to 60 million years ago, the plate have been drifting apart. So what we are looking at is actually the remnant of active rifts, where there used to be a source of heat, which is now gone, and we're actually looking at the remnants of all these rifting processes in rifted margin or a passive margin. So as an example here, you can see on the right hand side a depth section of the Southwest Barents Sea, where you can see large variation of crustal thickness going from here in the Bjørnøya Basin, very deep sedimentary basin, up to 10-12 kilometers, and moving really quickly to structural heights where actually the crust is almost preserved. So actually this part of the world is quite complex because you have a lot of structural, a lot of tectonism, and remnants of past volcanism. So that makes it actually quite notoriously hard and difficult for actually MT to interpret this remnants of active heat. And so in this project, we actually trying to use NT to find out what could be the contribution of finding the electrical resistivity of such geological contexts, and what could it bring as a new knowledge for the understanding of rifted margin. So this is the Southwest Barents Sea and the bathymetry, and all the dots that you can see here is actually receivers that have been dropped on the seabed to record this electromagnetic field over the past decade. And I was lucky enough to have access to this industry database that was initially used for exploration purposes. So I got access to all this database, and of course, in the framework of a PhD, I could only use only a subset of this. So I tried to sample the most important geological tectonic structures by actually extracting some profiles. So you can see here that's the dots are the receiver that I selected for my research, and you can more or less, perhaps if you're used to working on rifted system, I see it as a seismic OBS type of profile. So in terms of depth sensitivity and lateral extent, you see you go regional, and you can go up to the upper mantle in terms of sensitivity. So that could be really a good way to look at this data. So not going into detail, but that's what the empty data looks like in a pseudo section, as we call it. So you have on the vertical is the time period. So the period of the signal. So as you go to long period, you actually move to a larger depth sensitivity. And so each vertical stripes represent a receiver data. So just as a first observation that you could see is like you have actually a very dramatic variation at key tectonic boundaries, which means that this industry data that were not meant to investigate that depth were actually containing a lot of information on the tectonic and on the structural elements of the Southwest Barents Sea. So now, after introducing the data and talking about how it was acquired, I will move on to the modeling part. So what kind of treatment I gave to this data, to this empty data in the context of rifted margin. So what I will show you is actually a selection, even a more subset of this data that have passed through a 3D inversion process. So what you can see, this dark line is actually the section through a 3D cube, inverting for the data that you can see here with my pointer. Going north-south, so crossing deep basin and structural heights. So this is what you get when you perform 3D inversion of empty data. This is a electrical resistivity section. So where red is very resistive and blue is actually very conductive. So the first observation that you can make while looking at this model is actually that where the crust is very thick, very old and granitic, the resistivity is very high, which is quite expected. But when you move to this very deep sedimentary basin that have been rifted back in Eocene times, you can see that the signature of the sediments is rather very conductive, and you can see in my pointer here, this C2 anomaly is actually giving conductivity, a resistivity value below 1 ohmmeter, which is a rather strong indication of a very conductive material at this depth. So this remains to be explained at this stage. So when you get this model, you can look at the different type of data that you have. For example, here reflection seismics, gravity modeling, magnetic susceptibility. So all of this confirm that the conductive anomaly is actually occurring deep in the deepest sediments of this sedimentary basin called the Bjørnøya Basin. So this actually conductive anomaly comes from sediments that were actually syn-rift, so deposited as the rifting was occurring, which is back in early Cretaceous times, by the way. So that was an interesting observation, and based on this, I actually tried to refine and investigate whether this anomaly was actually real. Is that an artifact? What could it be? So moving on from this 3D inversion, I actually tried to go into a bit more, let's say, explore a bit more the model solution using a Bayesian inversion. So when you get this 3D deterministic inversion, you actually get one unique model that explain the observed data. But actually, there's there's a lot of non-uniqueness in this inverse problem. So you may have a lot of different resistivity model explaining the data. So when you move on to Bayesian inversion, you actually generate, let's say, 10,000 model that would actually honor the observation. And by generating all this model, you can make all kind of statistics and confidence and uncertainty on the anomaly that you see at depth. So this
You've
was
used
done.
10 minutes now.
Yeah, thank you. So this is a 1D Bayesian inversion, and what you can see here is actually that this very conductive anomaly is confirmed, and it's actually occurring well into this early thin rift sedimentary sections that are actually marine shales and most likely full of water. So, which leads me to the interpretation part and talking a bit more about geology and rifting processes. So what is this? What on earth is this highly conductive sedimentary section? And also this conductivity beneath in the upper mantle and the crust. Could it be minerals? So there's an absence of intrusion in this basin, so we haven't seen any evidence of intrusive activity there. Partial mets are absent. The active rift is long gone, so there's no actually melts or any source of that can be source of high conductivity. So we are left with the interstice fluids that's contained in the pores of the sediments. So actually, based on this, I will actually go trying to get more into the fluid properties that could be contained in these sediments. So I think we've heard it in the last presentation in the question. So in this case, I'm using the Hashing-Strickman model that uses a two-phase rock fluids medium. And it's actually an analytical solution and gives you the resistivity of this effective media. So you have a fluid that has a certain salinity or conductivity and a mineral matrix. And it's assumed in a connected pore network. So what you can actually see is that in the condition of deep sediments at depths of 9 kilometers and a porosity of 5%, which is rather high, the salinity of the fluid has to be higher than seawater to account for this conductivity anomaly. So how is it possible to enrich a fluid in saline elements at these depths, considering that these sediments were deposited in a marine setting, so seawater? So this gives me to the model I proposed, which is based on the serpentinization of this highly stretched crust. So based on also an analytical model, I can actually support this explanation by saying that a partial serpentinization of the upper mantle would actually create could actually result in a salt-enriched residual fluids by consuming pore water, and would actually support this bulk resistivity anomaly in the deeper sediments. So this is broadly touched upon, but this is actually what the preferred model I've defended in my thesis. So you have also field evidence of this in abducted system in the Alps or in the Pyrenees. You actually know, looking at saline inclusion in this cindery sediments that's been abducted on mountains, that they have actually higher salinity than seawater, and they contain elements of mantle reacted fluids. So there's indication that fluids were moving up from the upper mantle to the deeper sediments, which gave me this geological model at the end, which is the Bjørnøya Basin at the time of rifting. And I actually defended that this marine shales were actually the seawater from this marine shale were actually going through the upper mantle in a detachment fault and reacting with it and giving rise to serpentinization and higher salinity of residual fluids. that would explain the seismic and the resistivity model from 3D in empty inversion. So with this, I will conclude by actually pointing to the papers that have been published in this work, and of course thanking my supervisor and collaborator that you can see named here, and EMGS for giving me access to this fascinating data. So there's much more to be done, and that's where I've been ending in this project. So thank you very much for your attention.
Thank you very much, Romain. Do we have any questions for Romain? Derek?
Yeah, thanks. I didn't quite catch the sort of independent evidence for the serpentinization that you were showing. You showed some of these field analogs, which I followed, but then directly beneath your sediments, what was the other evidence, like seismic imaging for the serpentinization?
Yeah, so the evidence from other data was actually the gravity. You can see here. So this is the gravity modeling from Jernigan et al. And it actually shows that actually the density values and the magnetotic susceptibility are actually compatible with the serpentinized mantle.
Okay,
that's what I meant. Yeah.
Kathy.
Yeah, thanks. Really interesting talk. When you're so close to the magnetic pole, were there any challenges in obtaining the magnetotelluric data from what you measured at sea, given that you're not very good in the sort of far field approximation?
So I haven't seen evidence of this high latitude disturbance in the data I have in the Barents Sea. I'm not able to show you some evidence right now, but I haven't seen any sort of distortion on the northern on the
okay, thank you. Yeah, really interesting.
Sasha?
Yeah, thanks for this great talk. I remember porosity depth relationships in sedimentary basins where we drop below 1% porosity really quickly at a few kilometers, and probably there's a lot of spread in that. I'm not an expert in that, but could you think of any alternative possibilities than having this high porosity? Could you also have connectivity because of different kind of minerals that are there, some phase reactions? Can you explore this alternatives a little bit for me, please?
Yes, so thank you. So actually, just to clarify, so I'm assuming a 5% porosity, which is actually very conservative. So it's most likely very much lower than that. So it means that the salinity would have to be even higher in the real world. But no, that's correct. So minerals could be absolutely conductive media in this setting, but from the seismic evidence and from all the gravity, and I mean, so far, for example, mineralization due to intrusive seals, for example, have not been imaged. So I cannot really elaborate on this because they have not been observed. And a second possible alternative that I haven't touched upon here could be purely diagenetic processes, which are actually very poorly understood. So just by the effect of compaction and burial, you could actually break up some minerals within the shades and release potentially some fluid that have this type of salinity. But this is not documented so far. So I leave it open